Alrighty. My name's Dave McDermott, and what I did was I actually took a microprocessor and built a weather station. Alright. The problem we have with race cars, because we're using an internal combustion engine, we actually have to maximize the air-to-fuel coefficient that goes into the motor. And what happens is, when the air density changes, it changes the amount of air that actually goes in the motor, but also when the amount of water in the air changes, that also affects how much air goes in the motor. So what we did was, I took a microprocessor, made a weather station, so that wherever we are on the track, if I'm in line waiting or in a pit, I can cue and get an exact, at that instantaneous read, what the weather is doing. The bit, let's see. I basically took I simplified down the stoichiometry of chemistry, and basically what I did was that the way it works is for dry air, we have our fuel plus air gives us our combustion. However, when we put water in, that displaces the air and we get hydrogen coming out, which we don't want. Because what happens is that hydrogen comes out of the fuel because water doesn't burn. So the problem is water goes in, water comes out. It doesn't burn, so we lose power. So what we do is we take fuel away, get rid of the hydrogen, and it gives us oxygen out. And what that means is we've now, instead of having excess fuel, we now have excess air, making a limiting reagent. So what this does, the weather station actually allows us to know exactly how much water is in the air and how to customize our tune to know how much fuel to put in the motor. The thing is, the way cars are, we have to dial within 1/100th of a second of what the car is going to run. So we have to know what the car is going to do when we go make that pass. 1/100th isn't much. That's 0083 right there on a finished margin. So we have to be within a very tight margin to be able to say, okay, this is what the car is going to do. The car has to go do it. We have to be able to predict that, and from there on, it's the driver's part. But the main part is we have to be able to predict what the car is going to do. What we've been doing since 1987, which was before my time, when my parents started racing, was we used an aircraft altimeter and an analog hydrometer and thermometer. The problem with this is, back then it was all fine and dandy. But now the digital one stations, they're $500 to $800. Instead of buying that, I'll just go make my own. But the problem with the old school way is it's recorded pit, so if we're waiting in line, we can wait up to an hour. Weather changes a lot in an hour. And since it's not portable, it makes a problem there because we can't get what the weather is when we've been in a delay. The one alternative has that we found earlier this year was there's a website that keeps air density tracked for us. From us, they run off the airport, and I know it's plan blank. The problem is the airport only updates every hour. So what we found was that if we only update every hour, that was just like if we were using our old stuff, or if we got in a day, we're out of luck anyways. So the solution. I take an Arduino. It's based on C++ with an open source interactive development interface. And what was this Arduino there? It was brought by two different creators in Italy to increase the hobby of consumer-made electronics that can be programmed. So what I did was for the weather sensors, this is actually the easiest part of the project, was picking my sensors. Because I know, based on what the National Oceanic and Atmospheric Administration, they provide formulas for calculating everything I need to know. All I need is the barometric pressure, the temperature, and humidity. So those are the two sensors I need because the BMP 085, it does barometer and temperature at the same time. So I only actually needed two sensors. And this one right here, this one does barometer and temperature, this one does humidity. Now what I had to do was, okay, how am I going to get that data? So what I end up doing is I have a Bluetooth module over here where it'll actually log to my phone, and I can queue up at the 800 feet away, actually tested, and get the data from that box layer 800 feet away to my phone. And what I do is I said, well, if I'm going to be logging this weather, I need to know what time it is. So I took a real-time module, and the thing is, the thing with the real-time module is a processor only keeps time when there's power applied. And just like the desktop computer keeps time when the power outage is occurring, is there's a dedicated battery that sits in this holder right here and keeps the ticker ticking on its own processor to keep its own timestamp. Showing up on my screen now. Alright. And this is what it actually looks like inside this box. It's a little messy what's inside the box, but this is what it actually amounts to. Is what I have here is I have a power regulator coming in because I have 9 volts coming in. I have to get down to a 5 volt microprocessor voltage and a 3 volt sensor voltage. So what I do is I have a stepper and goes down to 5 volts on this side and goes to a power line, and 3 volts on this side. It has a power line going across the top. And what we do is this is the Arduino microprocessor, and it's a 16 megahertz processor, so it's not fast by today's standards, but it's fast enough to do what most robotics need it to do, automation. So what I do is I have a Bluetooth module up here, I have a temperature and barometer there, humidity here, and I have my real-time clock up here. Now the reason I have this kind of pushed away is because the time clock oscillator will become affected by any voltage pulse that's occurring near it. So I had to isolate it from any voltage lines that are near it, that way it'll actually keep an accurate timestamp. Then the other problem it has is interfacing a 3 volt sensor with a 5 volt processor. I have to have a logic leveler right here that will take that 5 volt signal and bounce it up to a 5 volt that the microprocessor can read.
What happens if the voltages don't match their specifications?
The sensors will, if the voltage gets too low, the sensors will start doing drop bites, or if the voltage goes high, it'll fry the chip on it.
In other words, you've got to make certain all the numbers match or it's going to catch fire.
It's basically what it amounts to.
So he has 2 circuits in there, power regulator and a logic leveler, which makes certain that all the levels of volts go to all the components correctly so that the system doesn't catch fire or lose power. So it's not just as simple as plugging it in like Legos. You have to say, oops, now I've got to do a little balancing act with my formulated regulator to make certain that all the electricity in my circuit is at the right levels.
Right. So this is how it works. We have a nice little flow chart here that I made up. And basically what we do is when the power is applied to the board, that starts the sequence. The first thing it does is run a setup program, which will initialize the serial and every other communication that occurs within the microprocessor. The first thing it has to do before it can actually run any executions is get calibration data for that temperature and barometer sensor. Once it has done that, it will run into what's called a loop function in Arduino, which is exactly what the name implies. It will sit there and loop anything inside that function over and over and over until there's some reason for it to stop. Usually there is no reason unless we're using a while loop or some other reason to make it cancel. So what does inside this loop is we get a decision right off the bat. There's a define in there I've made that's an interval. And what interval does, it says, I do a query to the microprocessor. Okay, here's a time since last boot. If I want to update every 5 minutes, that's 300 seconds. So I say 300,000 milliseconds is when I'm going to do a new iteration. So when the boot time is not an interval of 300,000, I get a no, and that goes to my incoming serial. So what I can do is, if I want my phone to update on my own, I can type the letter U on my phone. It'll hit this manual update, and then it'll actually run back and go back, follow this, yes, it'll go back through, and it'll come back and run this loop. Even though the interval hasn't passed, it'll come back in and run it for me and get me that current weather stamp. If that interval has passed, what it'll do is we'll get an automatic yes here, and it'll read the temperature, compute it, then read the humidity sensor. Now what I have here is a decision, because the humidity sensor may come out with a bad value if for some reason there's a bad voltage or something come in weird. So what I do is I have a catch right here. It says, is it in the correct range? Is it between, I put the humidity between 0 and 100%. I actually expanded the bounds a little, said negative 25% to 115 to give for any almost oddball for in a mineshaft condition type of situation. Or if it's fog or raining, in case the sensor has some strange offset I have to account for. So if it's not in range, it'll come back and read it again and and it'll do that until it gets the correct value in that range. Once it is in range, it comes back up, and I'll read the barometric pressure, compute the barometer, and then from there, I now have my temperature, my humidity, my barometric pressure. I can take formulas from the National Oceanic and Atmospheric Administration and say, okay, I can now calculate the vapor pressure, I can now calculate the air density altitude. So now I have all the stuff I need to have to get a current weather report, and then I get the time from a real time clock, that way I can put a timestamp on it. Next thing I do is I do a transmit over to serial. This is what sends it to my phone or my laptop or whatever I have connected to Bluetooth at the time, using my phone at the track. So what I'll do is it'll send that data, and then my phone will receive it by that serial connection, display it on my phone's screen. But what it also does, it'll come back to the incoming serial data. That way, if I need to actually do a double update for any reason or set the time, or if the real time clock is an error, I can do a memory dump and reset the time. And it comes back around and redoes it all over again. Alright, now this is how sensors communicate. Because the way the microprocessor reads is not necessarily as an analog voltage. Some sensors can. I prefer the more accurate, which is actually digital. And what it actually does is each sensor has a 7-bit address. And what happens is the microprocessor sends a key and it says, okay, I want this information from your sensor. So we can go and say, okay, it'll send that start sequence. It'll send the address for that sensor, and it'll ask that sensor, do you have data for me to look? So it'll say address, and RW, this 8 byte, is going to be a read command. And it'll say acknowledge. So now the sensor over here says, okay, I've acknowledged this ACK bit, so now I will send you data. And that's what this area right here is, and then the sensor sends an acknowledged bit, and it starts back over where the processor reads it. So that's how the processor reads the data. Now the only exception is the humidity sensor. It doesn't work this way. It actually has a frequency generator where it takes a value off the sensor, converts it over to frequency, which I now have to have the microprocessor read that frequency to get me the current humidity value. But most every other sensor in the system and in most robotics will be on I2C. Now how that goes from my processor to my phone. This is called serial, which some of us may be familiar as being a DB9 or RS-232 port on the back of the computer. Pretty much obsolete nowadays, except for in applications like this, where we need a data receive transmit simultaneously. And the way this works is that on the microcontroller over here, we have a transmit coming out. This is the data coming out of the microprocessor being received by my phone. And when I send something that says I want to set the time or I want to get a manual update, the phone will transmit something that the microprocessor will now receive. The code.